Hello students, welcome to 14th lecture of chemical bonding and molecular structure. So in last lecture our discussion was about hybridization of molecules, and we discussed some of the examples having sp, sp2 and sp3 type of hybridization. But all of those examples contain same type of hybridization for all the atoms present in the molecule. Now let us start with example in which we have different type of hybridization of carbons present in same molecule. So here we have a molecule which contains total 1, 2 and 3 different carbon atoms. And name of this molecule, we have total 3 carbons, so it will be propane, and we have double bond between first and second carbon, so it will be prop 1 in. Okay, so this is propane molecule, prop 1 in molecule. And now let us try to find the hybridization of carbons present in it. So as we can see, we have total 3 carbons, first, second, and this will be our third carbon. So let us talk about the first carbon first. So for first carbon, we have 2 single bonds with hydrogen and a double bond with carbon. So as we know, in excited state of carbon, carbon will use its 2s and 2p orbitals, and electron of 2s will jump in 2p, so we have total 4 single electrons. One bond will be formed with hydrogen, so hydrogen will provide its electron, second with hydrogen again. Then next we have 2 bonds with single atom, which is carbon. So with carbon it will form double bond, so second carbon will share 2 of its electron. So this is our electronic configuration of carbon 1. So first bond is sigma bond, second is also sigma, and this bond of a carbon is also sigma, because first bonds are always sigma bonds. So here we have total 1, 2 and 3 sigma bond pairs. And last we have pi bond pair. As we know, we need not to count pi bond pair electrons in hybridization. So in this case, we have one sigma bond pair in s orbital and 2 sigma bond pairs in p orbital. So hybridization of first carbon will be sp2. Now for the second carbon, so as we can see, second carbon contains double bond with first carbon, one single bond with hydrogen and one single bond with third carbon. Okay, so that's how 4 bonds of second carbon completes. Again same thing, we have 2s and 2p orbitals, electron of 2s will jump in 2p, so we have 4 single electrons of our second carbon. With hydrogen it will form a single bond and pair is complete. With this first or third carbon, it has single bond, so pair is complete. And with first carbon it has double bonds, so first carbon will provide 2 electrons for bond formation. So as we can see, we have one s orbital bond pair, then again sigma bond pair in p orbital, again sigma in p orbital, and this one is pi, so no need to count it. So again hybridization of second carbon is also sp2. And now for third carbon, so as we can see, third carbon has 3 bonds with hydrogen and 1 with second carbon. So structure of third carbon will be 1 bond with carbon and 3 bonds with 3 different hydrogens like this. And as we can see, all of them are single bonds. So it has ethane like molecule hybridization. So one bond with one hydrogen, second bond with second hydrogen, third bond with third hydrogen, and each hydrogen will provide 1 electron, and with carbon one single bond. So all of them are sigma bond pair electrons. So we have to count all of them in hybridization. So we have one s orbital and 3p orbital. So hybridization of this carbon will be sp3. Okay, so as we can see, we have 2 different type of hybridization, sp3 and sp2 in single molecule. Now what about if we have molecule like this? So in this case, this carbon has exactly the same hybridization as we discussed in previous example, and it was sp3. So we are not going to repeat it again. Okay, so we have sp3 hybridization for one of the carbon. Then let us talk about this carbon. So this carbon has one single bond with one carbon, one single bond with hydrogen, and then double bond with next carbon. So obviously it has 1, 2 and 3 sigma bonds, and second bond will be pi bond. So obviously this first bond, let us say it forms in s orbital, this will form in p orbital, and this third bond also forms in p orbital. Okay, so we have sp2 hybridization of this carbon. Now let us talk about the second carbon, because it has some different situation. So first of all, it has double bond with one carbon and again double bond with other carbon. So electronic configuration of this center carbon will be, it will have 3 single electrons in excited state like this, and it will form double bond with first carbon like this, and again double bond with second carbon like this. So each carbon will share one electron towards the one bond. So they have double bonds, so both of them will share 2 electrons. Now first bond are always sigma bonds, so these two will be sigma bonds. Second bonds are always pi bonds, so this bond and this bond will be pi bond. So we have 2 sigma bonds and 2 pi bonds in this case. And as we already know, we have to count sigma bond pair electrons and non-bonding electron pairs. But we don't have any non-bonding electron pairs here, so only count sigma bond pair electrons. So we have one sigma bond in s orbital and one sigma bond in p orbital. So hybridization of this carbon will be sp, and this last carbon has sp2 hybridization. That means this carbon has sp3 hybridization, next one is sp2, then sp, and last one is sp2 hybridization. So as we can see, in the same molecule we have total 3 different type of hybridization, which we already discussed. We know we have sp hybridization, sp2 hybridization and sp3 hybridization, and all of them are present in this single example. Okay, so as mentioned earlier, each and every atoms present in the molecule have their own separate hybridization, and here is an example. Now let us move on our next point, use of d orbitals in hybridization. So next is a hybridization of elements involving d orbital. Now in certain cases, certain elements do have d orbitals, but they will be empty, and that's why we are not mentioning them in electronic configuration of that element. With example, let us say for chlorine. So electronic configuration of chlorine is 1s2, 2s2, 2p6, 3s2, 3p5. So as we can see, in this electronic configuration we didn't mention d orbital, but it will be present in chlorine, because when we start third orbit, all of the possible L values or orbitals will be present. That means we know that if quantum number n, principal quantum number n is equal to 3, then you will get 3 possible value of L, which is 0, 1 and 2. So 0 represents s orbital, 1 represents p orbital and 2 represents d orbital. So that means for n is equal to 3, all of this will be present in the same atom. That means if 3s orbital is present, it represents 3p will be there and 3d will be there as well. Okay, although electronic configuration, suppose it is 3s1. So 3p will be there but it contains 0 electron, 3d will be there but it also contains 0 electron. So we are not mentioning them during the electronic configuration, but it is there. If a situation occurs, then the atom can use that orbital. So as we can see in this case, in case of chlorine, we have principal quantum number 3 and we have L is equal to 0 s orbital and L is equal to 1 p orbital in this case. So it must contain d orbital as well, but with 0 electron. That's why we are not mentioning it during the electronic configuration representation of chlorine, but it will be there. If chlorine requires, then it can use it. So as mentioned here, the elements present in the third period contains d orbital in addition to s and p orbital. Now third period, that means principal quantum number will be 3 for outermost orbit or valence orbit. So as we know, if 3s is available, then it must contain 3p and 3d as well. The energy of 3d orbital are comparable to the energy of 3s and 3p orbitals. All of them are present in same principal quantum number. That means they have comparatively less difference in their energies. But still, energy of 3s will be lower than 3p and energy of 3p will be lower than 3d. So energy of these orbitals are comparable, and that's why as a consequences the hybridization involved either in 3s 3p and 3d or 3d 4s and 4p is possible. That means if electrons are present in 3s and 3p orbital, then they can utilize 3d orbital, and if electrons are present in 3d orbital, then 3d orbital can utilize next 4s and 4p orbitals as well, because energy difference of 3d 4s and 4p is again comparable. Okay, they are comparatively close to each other. However, since the difference of energy of 3p 4s orbitals is significant, no hybridization involving 3p 3d and 4s orbitals is possible. Okay, so they have comparatively more difference. That means energy of 3p and 4s, they have large gap between them. So that's why they cannot be in same hybridization, because during the hybridization energy of all the hybrid orbitals are almost same. Okay, that's why it is not possible. The important hybridization schemes involving s, p and d orbitals are summarized below. Some short description is mentioned here with type of hybridization and examples and shape. Okay, so let us discuss it step by step. But again, same thing, you can find hybridization on your yourself if you know the electronic configuration of the atom. Okay, so based on the atomic structure, we can predict hybridization or we can find exact hybridization, but for that you have to know about electronic configuration of given atom. So let us observe this. Here we have dsp2 hybridization. That means d orbital is mentioned first. It represents, it will be 3d orbital. Okay, then s orbital, that means next it will be 4s and then 4p. Okay, so this represents 3d 4s 4p orbitals will be used in this type of hybridization, and shape of the molecule will be square planar. And total number of orbitals, as we can see, we have one d orbital, one s orbital and two p orbitals. So total we have 4 different bond formations. So this will be atomic orbitals, and examples are mentioned here. Nickel Cn4, Cn represents cyanide ions, and this square bracket represents, it is coordination complex molecule. Okay, you will learn about this coordination complex molecule in standard 12. There is a dedicated unit about these type of molecules. So based on the name, coordination covalent compound represents they have coordination covalent molecular formation or bond formation. So square bracket represents anything inside the square bracket has coordinate covalent bond between them. That means nickel is a metal, so it do not have extra electrons, but it has empty orbitals. Metals are electron donating elements or electropositive elements, so usually it will donate the electrons, and they do not have comparatively high quantity of electrons. So nickel will share its empty orbitals, and cyanide is a negative ion and it has some extra lone pair of electrons, so it can donate it in empty orbital of nickel, and there is a coordinate covalent bond because both of the electron belongs to cyanide only. Nickel do not share its electron. So that's why these type of molecules are generated, which is known as coordinate covalent compounds, or in short, complex compounds. Second example, trigonal bipyramidal. So as mentioned here, we have one s, 3p and one d orbital. So orbital will be, let us say it will be 3s, 3p and 3d. Okay, so in this case we have pf5 and pcl5 like molecules. Shape of molecule will be trigonal bipyramidal. Then we have square pyramidal, dsp3, that means 3d, 4s and 4p orbitals will be involved. And example BRF5 and XeOF4. Here we have xenon compound, which is usually non-reactive. Xenos is non-reactive, but if you have strong elements like oxygen and fluorine, they are one of the most electronegative element, then they can even make normal gases reactive, and then they can form bonds between each other. Lastly, we have octahedral shape containing two hybridization, sp3d2 and d2sp3. That means sp3d2 represents there will be 3s, 3p and 3d orbitals involved in hybridization, and d2sp3 represents it has 3d, 4s and 4p orbitals involved in hybridization. Number of orbitals are same, shape of molecules are same in both of this example. And here we have few examples mentioned: SF6, CRF6 3 minus, CONH3 6. So note here, here we have total 4 orbitals, 1d, 1s and 2p. So central atom will combine with 4 other atoms. Here we have total 5, 1s, 3p and 1d orbitals. So central atom will combine with 5 other atoms or elements. In this case dsp3. Again we have 5. So as we can see, Br is attached with 5, and here xenon is attached with 5 other elements as well, or 5 bond will be formed. And last octahedral, here we have total 6 orbitals, 1s, 3p, 3 and 2d, and second case 2d, 1s and 3p. So again both of them contain 6 elements, orbitals. So central atom will combine with 6 other atoms. So as we can see, in all of these cases we have 6 other atoms or 6 bond formations. Now let us talk about one hybridization, sp3d type. So molecule as mentioned here, it is PCl5. So ground state electronic configuration for P or phosphorus is as mentioned here. It has 3s orbital with 2 electrons and 3p orbital with 3 electrons. This element belongs to nitrogen family, so it will have same electronic configuration. For nitrogen we have 2s2, 2p, 3 electronic configuration, and second member of the group will have 3s2, 3p, 3 type of electronic configuration. So as we can see, third orbit is already started, so it must contain 3d orbital as well, but because of 0 electron we do not usually represent it or mention it. Now electron pair present in 3s orbital will shift its electron in 3d orbital, and because of this type of shifting, excited state of phosphorus will have this type of situation. That means one single electron in s orbital, 3 single electrons in p orbital and 1 single electron in next 3d orbital. So total number of orbitals 5. 5 orbital contains single electron, so it needs 5 other elements to share their electrons with central phosphorus atom. That's why chlorines will share their electrons with a single electron of phosphorus, and pairs will be completed. So as we can see here, we have 5 different electron pairs, and in each of these cases, first electron, let us say it belongs to our central atom P, then second atom electron represents the electron of chlorine. Same is applicable for rest of the pairs. And as we know, all the single bonds are sigma bonds. So these 1, 2, 3, 4 and 5. All of these 5 bonds are sigma bonds. Okay, and we have to count sigma bonds in hybridization. So hybridization involves 1s orbital, 3 p orbital and 1 d orbital. So hybridization will be sp3d, and as we can see, we have total 5 orbital, and shape of this molecule will be triangular bipyramidal because it has sp3 hybridization. So same description is mentioned here and shape of molecule is mentioned in this image. So as we can see, we have PCl5 molecule, and in this case we have 2 different type of bonds and 2 different type of bond angles. Although central P is connected with same type of 5 chlorines, but still they have different environment. Not all the chlorines are attached equally. They have different energies because of difference in their bonds and bond angles. Now as we can see, we already discussed about these type of shapes or trigonal bipyramidal shapes with 3D figures in earlier lecture. Okay, so you can go and refer that if you have any confusion regarding to shapes of this molecule. But in short, let us quickly repeat it as it is mentioned in this point as well. 3 chlorine present here are called equatorial bonds. Their bonds are called equatorial bonds. And between them, if we observe it from the top side, then it will appear like this. At the center we have phosphorus and at the corner we have chlorines. So if we connect P with Cl, then we know that this bond angle will be 120 degrees. So here we have one 120 degree bond, second 120 degree bond, and third 120 degree bond. Now this top and bottom chlorines are called axial chlorines or axial bonds because they are present on imaginary axis of this triangle, passing through this triangle, and this line or axis is perpendicular with our plane of triangle. So perpendicular, that means it contains 90 degree bond angle. So we have 190 degree bond angle at the top and 190 degree bond angle at the bottom for this bottom chlorine. So as we already know, as the bond angle decreases, it decreases the distance, and if distance decreases, then repulsion or attraction increases. So these chlorine elements will repel each other because of similar nature, and if bond angle is short, that means repulsion will be high. These 3 chlorines are at 120 degree bond angle, so their distance are comparatively more, and these 2 are 90 degree. That's why they will feel more repulsion from the electron pairs, and that's why because of more repulsion they are stretched. Okay, these axial bonds are actually stretched and they are comparatively longer than these equatorial bonds. That means these 1, 2 and 3, these 3 are equatorial bond, and these 1 and 2, these 2 are axial bonds. Okay, so axial bonds are comparatively stretched because of shorter angle and they are comparatively weak. And we already discussed this point earlier with 3D structures, and same thing is mentioned again here. Okay, so same description is mentioned here. You can go and read it. Next example is mentioned for SF6, and as mentioned sp3d2 type of hybridization. This hybridization gives us octahedral shape, and we already discussed about octahedral shape. Again, you can refer it in the same lecture as you can refer the previous example, that means trigonal bipyramidal. Okay, so you can understand both of them if you have any doubts. So go and check that lecture if you have any confusion. So let us move. How can you find the hybridization of sulfur in SF6 molecule? First of all, you need to find its electronic configuration. So sulfur belongs to oxygen family, so just like oxygen, it will have same type of electronic configuration, but its principal quantum number will increase with +1. That means if oxygen contains outermost orbital electronic configuration as 2s2 2p4, that means sulfur electronic configuration will be 3s2 3p4, outermost electronic configuration. If it contains third orbit, then it must contain 3d orbit as well. So that means electronic configuration of sulfur is something like this. It contains 2 electrons in s orbital and 4 electrons in p orbital like this, 1 pair and 2 single electron, and d orbital will be completely empty. Okay, so right now this is its electronic configuration. During the excited state of sulfur, pairs will break down. So we have 1 pair in s orbital and 1 pair in p orbital. So it will split and electrons will jump in d orbital in excited state. So this will be the excited state of sulfur. Now as we know, in SF6 molecule 6 fluorines will be attached. So each fluorine will share its electron with single electron of sulfur like this. Okay, so fluorine will be attached like this, so that means it will donate its electron for pairing as well. Okay, so this will be the situation for SF 6 molecules. Now let us count the hybridization. So as we can see, each pairs are sigma bond pair, and you have to count all of them because they all are sigma bond pairs. So one sigma bond pair in s orbital, then 3 in p orbital, and 2 in d orbital. So hybridization will be sp3d2, and remaining description will be about octahedral shape. We know that octahedral shape has 90-degree bond angles. All of them are same, and that's why all of the fluorines are exactly same. Their energies are just like each other. Not it is not like previous example in which we have two different type of chlorines. Some are more stable than others. Okay, so hybridization and structure and electronic configurations are mentioned along with structure of sulfur. So you can go and check it yourself. Description is already given to you. In next lecture, we will move on our next theory, molecular orbital theory. If you find any difficulty in hybridization, feel free to ask and try to find hybridization of some molecules yourself. And keep in mind, we have to find hybridization for covalent molecules, not for ionic ones. Ionic ones do not have this type of hybridization. Only covalent molecules have. Okay, so try to find hybridization of some simple molecules and use some slightly complex example as we discussed in the earlier portion of this same lecture. Okay, if you find any difficulty, feel free to ask and we will discuss in detail with suitable examples. Thank you.